Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hello, I'm Kenton McHenry, and I'm presenting this work on behalf of my colleague, Rob Cooper, who's leading our work on document analysis. So what we're concerned about here is basically the ability to compare documents. How do we know one document is similar to another document? Are there groups of documents that share similar content? And then, once we have such ability, can we do this in a scalable manner so that we can process a large amount of documents? So our work is sponsored by the National Archives. It's basically, what they're responsible for is any decision, all the paperwork, all documents that were involved in any government decision has to be archived, and pretty much in perpetuity, forever. And this consists of many physical documents, but it also consists of many electronic documents, which is our main focus here. Given this large amount of documents, you need to consider several things. So one is, do you really want to even save everything? In reality, there's likely many duplicates of the same document as a document is shared among different distributed users. Maybe a memo passed around, a paper. Also, there's different versions of that same document. So perhaps a paper is being passed around and revised by different people and passed back and forth and back and forth. Do you really want to save all those documents, especially as space is a constraint for you? Maybe only one of those is good, the last one, or maybe some sort of union of all the content in one pseudo document created from them. Who knows? So that's one of the questions to answer: what to preserve, and how to preserve. Again, do you want to keep everything? Well, that is the goal of the National Archives, but do you really want to keep everything if that's really something that's not really tractable at the moment? Do you want to keep some of them? Format conversion. So basically, if the same document exists in multiple different formats, do you really want to keep all of them again? It's the same thing. Do you convert to one of the formats? Maybe one of the formats is more accessible than others. Maybe it has a better chance of surviving through time. So if it's a proprietary format and the vendor goes out of business, that format, basically the content in that format is locked away. So those are issues we need to consider. So identifying what to preserve. So basically, this is the problem we're at hand. We have a bunch of documents, and they're just a pile of documents. What we want to do is basically organize those documents automatically. In this case, those documents I showed earlier were actually from 3 different documents, where the first document had 3 different versions, the second document had 2 versions, and the last document only was by itself. And we would like to do this in an automated manner, so that after the fact, we could decide what we want to do with these duplicates, version duplicates of the same document. So we need the ability to automatically determine similar documents. So to do this, we have to be able to compare documents, and we have to ask the questions: what makes 2 documents similar to one another? Is it the text? Is it the authors? Is it the images within there? How do we identify 2 different versions of the documents? So once we can compare 2 documents together, how do we know if it's the similar version? Because they're clearly going to be different, little tweaks here and there. And then once we do that, how do we choose one document to represent the entire group if we only want to save one of them? And then scaling this, because we're going to be able to have to deal with large archives here. How do we compare many documents? Can the previous solution be done in a scalable manner? And if so, can we estimate the time resources required to process a given data set? So if we have a large data set, can we suggest how many nodes of a cluster would be required to process this in under X amount of time? Or how much time would it take to process this on n nodes? Along those lines, can we bound those numbers? So we're going to focus on Office documents here. And basically what these are just containers of digital objects, mostly text, images, vector graphics. And these are the ones we're going to support, but there's other things like an HTML document, for instance, can have video, audio, 3D, who knows what. We're going to focus on one particular format, PDF. It's a fairly accessible format. There are libraries to access its content. It's widely accepted and used. So we're going to kind of focus on that. But we're not really restricted to that. We have dealt with other test archives with Word documents, and basically what we do in those cases is we convert to PDF documents, do our solution for PDF documents on those. With regards to the NARA project as well, we have done work with format conversions. There was a poster about our work today on that, and we'll have another presentation on that at the IEEE conference. basically of using this idea of imposed code reuse to basically gain access to file formats that aren't readily accessible otherwise by basically using the code within a binary and reusing it. So with regards to comparing documents, again, we're focusing on the text, images, and vector graphics within them. Basically, to do that, what we do is we split the document into these three constituent parts and basically compare each one separately and then combine them back together to get some sort of measure of how similar two documents are. So for text similarity, for instance, basically what we do is we look at the word frequencies within the two documents and we compare them together. Basically, when doing this, we consider more frequent words to be more important as it occurs more often in a particular document. So we consider that when comparing the two documents. For image similarity, basically we would look at the colors within various images. This is very simple stuff at the moment. And the idea here is we want to move towards scalability, and we have to keep that in mind. So basically, with regards to colors, what color values do we see? We put this into a color histogram, and we monitor the frequency of various colors. And we can do that. We've experimented with treating this on an image-per-image basis, but also we found that also treating all the images in the entire document as one super large image tends to work better, and there's reasons for that, which I won't get into here. For vector graphics, what we do is basically vector graphics are, unlike raster graphics, they basically are composed of lines and polygons and so on to make up an image as opposed to just pixels. We deal with the lines in such images, and basically we create histograms of the orientations of the various lines of the image and basically compare, again, those histograms to one another to get basically a distance between the two histograms and get some sort of weight difference between the two documents. So once that's done, we have these three separate scores for images, text, and vector graphics. We then combine them together, and we do this by weighting them according to the amount of area they occupied within the original document. So, for example, if the text occupied 50% of the document to begin with, it gets weighted by that amount. And if it occupied nearly the entire amount of the document, it would get weighted most importantly as compared to images and vector graphics. And then once we do this, we address the issues of actually finding groups of documents, different versions of documents. We do this by clustering these measures between the documents using some sort of conglomerate of clustering algorithm to just basically find groups of documents that are very similar to one another. So to visualize this, these are some results from a small test set of 10 documents where there are basically two documents, one with 3 versions of itself and another with 7 versions of itself in this test set. And basically the first plot here is of the image similarity between the two documents. The in-plane axes here are the IDs for the documents 1 through 10. And the axis coming out of the plane is the similarity score. The higher, the more similar the two documents are. So you can see the red stuff is documents that are similar to one another along the two plane axes and so on. And blue is very unsimilar. The next plot is of the raster image similarity. And the last plot is of the vector graphic similarity within this test set. So we combine these based on the weight. And the weight is dependent on actually the area occupied in both of the two images. So it's actually, it depends on both. That's why it has a shape that's not planar. And basically there's one for the text, images, and the vector graphics. And we use this to basically just add together 3 constituent weights to get the final comparison. And as you can see here, there are 2 standout groups. This is, again, the ordering has been shifted to make that more apparent. But a clustering algorithm would find that for us, ideally. So basically, you can see that there's these 3 groups. The dots are the actual points. There's 3 documents here that are very similar to one another, and there's another 7 documents here that are very similar to one another. So these are the 2 groups with the different versions numbers within the data set. So this is one of the things we want to do, be able to identify these different versions of the same document. Another thing we would like to do is basically verify the ordering of documents. So if you have different versions of a document, which one came after the other. So the most straightforward thing you could think of would be to just basically align them according to their timestamp. Timestamps can be changed, however, and when you're archiving, you want to make sure it would be beneficial to verify that kind of stuff. So what we do is we initialize based on the timestamp, but we use our comparisons to check the flow of content as we go through the time and see that it's consistent with what you would expect in a different as a version of a document progressed. So this is a tool here that we developed using the similarity measure that we have. Basically, along the columns here are different documents, and there's 6 different documents here. And along the rows is a particular piece of content, whether it exists or not. If it exists in that particular document, it's green. If it doesn't, it's white. So in this case, this is the first row. First set of rows here are images, and these represent 3 images that exist here, and they progress through the different documents, and then some other images are added here, and so on. So we do this with various features within the document. File size, the file size continuously grows. The document dates, we look for dates in the documents and see if they remain. Basically treat them as small features within the document we can track. Image count, sentence count, average data value. I'm not sure what that last one is actually. But basically we're looking for a consistent flow of this. And if not, we want to flag it so that a human could basically make the final decision. We don't want to. This is a difficult task to do completely automatically. We keep a human in the loop for this. And basically, they can then decide if that's correct or not. So in this example here, I believe this document was flagged as red here because the file size changed abruptly, so indicating a large amount of content was deleted and then added back, perhaps. And this is the same would apply for images. If an image was suddenly deleted, added back, that's not really consistent with the version change. You want to flag it so that an archivist could decide whether that's actually in the right order or not. So these are the kinds of tools we want to look at, and the idea is then, can we do this in a scalable manner? So we want to deal with large amounts of data, huge archives, and be able to process these documents in an automated manner. So this is not really practical on a sequential machine. So the similarity matrix alone, comparing every document to every other document, is an order n squared operation. As the number of documents increases, this number is going to grow rapidly. So we want to consider taking advantage of some parallelism. So to do this, we want to identify tasks within this that can be performed in a parallel manner, and we were keeping that in mind as we were developing this, and the techniques that we use for similarity metrics. For example, the individual document statistics, the frequency count of words, the color pixels within images, each of these things can be done independently. And basically, we can separate them out across various machines and compute them and then bring them back together later on. So that's only part of it. The next part would be the pairwise document comparison. Again, this is every document and every document, so we would have to break up this n squared operations into sub-sequences, but it too can be done in parallel, comparing various groups of those end-to-end documents. So there's various ways we can do this. One would be using something like a TeraGrid, or another solution is MapReduce. I'm going to describe both. So TeraGrid is basically a network of high-performance computers connected with high-performance networking. We have 4 of these computers that are part of this. It's made up of various computers around the country, and we have 4 of them at NCSA. There's more than 3,000 nodes available. The problem with this kind of solution, though it would be a possibility, is that access is not readily available to everyone. In order to get access to this system, you have to write a proposal, and it has to be accepted, and you get a certain amount of computation time. And we would like to develop something that can be used by anyone, pretty much, which is why we went towards the MapReduce paradigm. For those who don't know, this was introduced by Google to do parallel programming. To basically a cluster computing to do parallel processing tasks. Basically, what this involves is it works on problems that can be mapped into this MapReduce paradigm. Basically, if you can break a task into this map step and reduce step, where the map step involves some sort of master node splitting the task into smaller subproblems and then distributing them among the various nodes in the system, and then a reduce step, which basically takes all those solutions from the subproblems and combines them back together to one master output. If your problem can be broken into that, then this MapReduce paradigm is a way to go. Benefits to this is there's an open implementation for this, Apache's Hadoop, and then basically if you have a number of computers lying around, you can install this on that and have yourself a small cluster of computers. And it's basically a convenient means of utilizing parallelism. So in terms of our document analysis, the map and reduce step, what it would consist of is our map step would involve splitting the image into digital objects and actually splitting those into subcomponents. So basically for text, what this means is the actual words would be some components sent out to the various map nodes. And the images, this would be the colored pixels, and for vector graphics, the oriented lines. And basically what each node would do then is they would take these series of words, pixels, and oriented lines and basically maybe count them, sum them together, basically, just for the statistics that we're looking for. And the reduce step would basically take these sums and compute a final sum over all that stuff. So that's what would involved in parallelizing the statistic acquisition for our document analysis. So for our test bed, what we have is we have a small cluster where we just had 4 computers we had lying around. Basically, we created one small cluster for ourselves. It has 4 nodes with dual-core processors. Files replicated on all the nodes. And then we also tested it on the cloud computing test bed at the U of I. This is a large 64-node cluster with dual-core processors, and it was funded by the NSF, Yahoo, Intel, and HP. And again, files are replicated on the 3 nodes. So we tested basically on both of these 2 systems. So our test data, we have a small test set, which basically consists of 54 documents with fairly small document sizes, 3 pages on average, about 1,000 words, maybe 1 image, and a few 56 vector graphics per image. Well, this one has a large number, I guess. And a larger test set, though only 20 documents, the documents are relatively much larger, 248 pages on average, much more words, a large number of raster images and vector graphics images. So running on the, this is the small data set, and we basically want to compare the sequential version versus the parallel Hadoop version. And we're using Hadoop here. So the sequential version here is the one with no Hadoop, and it actually ends up running faster than the Hadoop version on the small data set. And this is due to the fact that when you're dealing with a small amount of data, there's a large overhead price that you pay for breaking up the file, splitting it among the various nodes, opening the file again and again and again, and so on. So the parallel version of Hadoop is right here on the right. In the middle, we have this extra graph where we kind of treat the parallel version as a pseudo-sequential version. Basically, we impose that every map step finished before and any other map step finishes. And you can really see the overhead that you're paying over the map-produced version here. So there's a huge overhead versus this. These are both sequential for all intents and purposes. And there's a huge overhead you're paying here. It's a lot less here because it's actually run in parallel as it was intended to be. So on a small data set, this wasn't really beneficial. On a larger data set, it of course is. So here's the no Hadoop version, the sequential version. And it's the running time for that processing, this time the large data set is far larger than on the parallel version. Again, running the pseudo sequential version, you can see that it's still longer. There's this overhead you're paying. But in parallel, because it's in parallel, you're gaining overall. So one thing we considered was that maybe we're also not taking full advantage of all the nodes that we have, that maybe some of the map nodes are actually being idle while waiting for other things to occur. So one thing we considered was also breaking up the document into pages as opposed to individual documents. So currently each map node gets an entire document to deal with, whereas it could be, why not just break it into pages and split those up among documents, hoping to better saturate the system. So we did that here. In this case, we're just, let me go to this image first. So this is we just took one file and split it up into various numbers of pages here along the x-axis here, 1 page, 2 pages, all the pages, 256 pages. And we tested it on our test beds. Again, we have the Hadoop, our own cluster with 4 nodes, and we tested with 1, 2, 3, and 4 nodes, respectively, and on the larger CCT test bed. And at some point, there is benefit in actually breaking up in pages, but the processing of this one document as it's saturating the system. But initially, here, whereas 1 page splits, you really don't. And we believe the reason here is because there's actually a large penalty in duplicating, basically opening the PDF file on each of the nodes again and again and again. So initially, by breaking in too small of a chunks, you lose. At some point, you do gain, but eventually, again, you start to, as you begin processing the whole document on each node, you lose again. So there is some benefit on a large file to break it up into pages on this cluster. So how do I go back? Okay. So on the small file, you pretty much get no gain, though, however. So again, all the overhead is in opening. The file was small to begin with. All the overhead in opening the file, again, in the various pages, it really gains you nothing. So it's something to consider when dealing with this. Though it does show, and one should believe that with large data sets, there is benefit to be gained with this. On small data sets, it's important to consider that there's not always a gain when processing the documents. So just some statistics on that one image. By far, the thing that took the most amount of time was processing the images at 265 seconds, and the text and the graphics were far less. And this is something to consider maybe along the way we were doing the images, a fairly simple procedure, counting pixels and comparing them. although that other procedures would be actually far lengthier in time. So work in progress. We're still working on a parallel implementation for the pairwise document comparison. Basically, what this involves is breaking up the n-squared similarity matrix into subparts and splitting that among different groups in the cluster, and then combining those again to rebuild the matrix. And currently, we've only done the first half of that, which is gathering the statistics. And also, it would be beneficial, since building these clusters, the number of nodes is clearly, there's cost involved, how many nodes you have. It would be convenient to have a tool, again, as I mentioned earlier, that could tell you, if you want to do this in a certain amount of time, how many nodes will you need to process it. So in the simple case, this would be as simple as basically taking the number of documents you have and dividing it by the number of nodes, and some cost per document would indicate how long this would take, and you can invert that to get how many nodes you would need. That's, of course, unrealistic because documents are different. So various documents are more complex than others. Basically, what you really need to consider are the number of words, the word length, if you're doing comparing word to word. That's something you need to consider. The number of raster images in pixels on average per image, the number of vector graphics, the lines within the vector graphics, the required conversions, if there's any conversions that are required, and the cost of those conversions. In addition, you need to consider the fact that the nodes may vary in the cluster as well. The CPU speed of those nodes, the available memory, the disk space, the latency across the network. And these are all variables that need to be considered when doing this, when building such a tool to estimate time and resources. And we're thinking that the way to do this was basically by creating small exemplar sets of the data, running it through this, measuring basically in some model each of these variables, and using that to estimate the overall time for a much larger data set, which the sample represents. Any questions?
Any questions for Ken? Go ahead. The large data set was pretty small.
It's relatively large, yes.
So much more impressive graphs
Yes.
if you had a bigger set.
No, yes. Not yet, no. We realized that as a relative. Yes, of course.
I'm interested about the similarity algorithm. Have you thought about extending that to other type of objects and not just documents?
So actually, in the conversion stuff we've been doing, it's been motivated largely about 3D conversions. And in doing that, we were interested in measuring the loss as we go from file format to file format to file format. So we do have been working on measuring 3D loss as well. And actually, we're planning on extending that conversion system to basically everything. So this document comparison would be a part of that, but we would also introduce methods of comparing audio, video. And again, this would pretty much be a survey of what's out in the literature, considering what's efficient and can be done in a practical manner.
And the second part of that question, have you thought about incorporating semantics into this process?
I don't believe so at the moment, no.
Okay.
Yes?
On your, I think it was the last slide, you had various characteristics that would affect the performance and therefore the scaling. Are you intending on building a performance model for which you might have coefficients against each of these that would predict given some rough cross-section of documents?
That would be the idea. Some sort of simple model to capture enough of the data set in order to make some sort of educated guess as to what a larger data set would entail.
And is that something you're going to do?
That's the direction we're planning on going, yes.
Are you planning to do any reprocessing based on the context?
Context, as in where it was located, or
Proximity,
that's not what we haven't considered that, but that is definitely something that is important. That would be something to consider.
Can you deal with file and file paths, right? So you're figuring out some metadata related to the source of these things. Track of that is
That would be important, yes.
Very good. Thank you very much.